this problem we have 1 kilogram of carbon dioxide that's being compressed from 1 megapascal and 200 degrees Celsius to 3 megapascal in a piston cylinder device arranged to execute a polytropic process for which PV to the 1.2 is constant. And we want to determine the final temperature, treating the CO2 as first an ideal gas and then as a van der Waals gas. So what we're going to do, first of all, let me just talk about this polytropic process. And I made a video on the polytropic process, so go back and watch that if you want some more information about that. But basically a polytropic process is a process that gas can be modeled with the following relations. Or the pressure and volume of a gas have the following relations. So PV to some constant is equal to constant. So the pressure and volume can be modeled as PV to the N equals C, and these are both constants. So if a gas can be modeled using this relation, then it's a polytropic process. So let's first calculate, well, first of all, let's draw a diagram of what we have. So it says we have a piston cylinder device. We have 1 kilogram of CO2, and it's compressed from, so P1 is 1 megapascal, and P2 is 3 megapascal. T1 is 200 degrees Celsius, which is 473 Kelvin. And we're looking for T2. So basically we're compressing this carbon dioxide. It behaves as a polytropic process, and we want to determine what the final temperature is. So the process that we're going to use is we're going to first of all calculate V1, and we're going to calculate V1 from the ideal gas law because, well, for the first part we're going to use the ideal gas law. For the second part we're going to use the van der Waals gas equation of state. So first we're going to calculate V1, and then we're going to determine V2 from V1, assuming that we have a polytropic process. So V2 is going to equal V1 P1 over P2 to the 1 over N. And I'm going to show you how I got that in a minute. And then for step 3, we're going to calculate T2 from the ideal gas law using the specific volume that we calculated in step 2. So calculate T2 from the ideal gas law. So T2 from ideal gas and also from van der Waals. I want to talk about this, like how did I come up with that relation? So since this is a polytropic gas, I know that, and it tells me that P1 or PV to the 1.2 is equal to a constant. I know that P1 V1 to the 1.2 is equal to P2 V2 to the 1.2. So what I want to do is solve this equation for V2, since that's what I'm calculating here. So I'm going to divide over the P2, so P1 P2 V1 to the 1.2 is equal to V2 to the 1.2. Multiply both sides, well, not really multiply, but raise the power of both sides to 1 over 1.2. So then what I'm going to end up with is V2 is equal to V1 multiplied by P1 over P2 to the 1 over 1.2. So that's how I got, this is 1 over 1.2. So that's how I got this equation that we're going to use here. And the reason why we're using that is because we're assuming this is a polytropic process, so this is the relation we need to use between the pressure and the volume. What we want to do is look up our constants. So first of all, R, and we're looking these up for carbon dioxide. So R, so the gas constant is 0.1889 kilopascal meter cubed kilogram Kelvin. The molar mass is equal to 44.01 kilogram per kilomole. The critical temperature is equal to 304.2 Kelvin, and the critical pressure is equal to 7.39 megapascal. And remember, these are just values that you're going to look up, so you don't need to calculate those. So now let's do step one. So step one was I'll just summarize them here. So we're going to calculate V1 from ideal gas, and then second we're going to use van der Waals equation of state, but we're starting with ideal gas. 2 is to calculate V2 from this, so V1, P1 over P2, 1 over 1.2, and then 3 was to calculate T2 from the ideal gas law, and then second from van der Waals. So I'm going to specify ideal gas and van der Waals, and same thing with this one. So ideal gas, whoops, I already wrote ideal gas. So ideal gas and van der Waals. Alright, so starting with the first step, and we're doing ideal gas first. So starting with the first step, we know that the ideal gas law is PV is equal to RT. And we want V1, so I'm going to specify that these are all 1. So V1 is equal to RT1 over P1. So this is equal to 0.1889 kilopascal meter cubed kilogram Kelvin multiplied by 473 Kelvin divided by P1, which is 1 times 10 to the third kilopascal. And we need, so it was given in megapascal, but we want to convert it to kilopascal because we have kilopascal in our gas constant. So the kilopascals are going to cancel. The Kelvin cancels, so we're left with meters cubed per kilogram, which is the unit that we want because we're solving for a specific volume. So this is equal to 0.089 meters cubed per kilogram. Now we're on step 2. So from the fact that we know this is a polytropic process, we know the relationship between pressure and volume, so we can calculate V2. So V2 is equal to V1 multiplied by P1 over P2 to 1 over 1.2. So this is equal to, so we calculated V1 up here. So this is equal to 0.089 meters cubed per kilogram multiplied by 1 megapascal over 3 megapascal. And this is 1 over 1.2. So this works out to 0.0356 meters cubed per kilogram. So now we can use the ideal gas law to calculate the final temperature because we know that P2 V2 is equal to our T2. So T2 is equal to P2 V2 over the gas constant. So this is equal to 3 times 10 to the third. So P2 is 3 megapascals. So this is 3 times 10 to the third kilopascals. And we want it in kilopascals because our gas constant has kilopascals in its units. This is multiplied by V2, which is 0.0356 meters cubed per kilogram, divided by the gas constant, which is 0.1889 kilopascal meters cubed kilogram Kelvin. So now let's cancel out some units. So the kilopascals cancel, meters cubed cancels, kilograms cancel, and we're left with Kelvin, which is what we want because we're looking for a temperature. So make sure when you're doing these equations, always write your units in, like always write your units as you're putting in the numbers, because it's an easy way to verify that you're doing things correctly. Because if you're not, like let's say you use the wrong gas constant, like let's say you use the universal gas constant instead of this gas constant, your units aren't going to cancel out correctly, and so you'll be able to catch your error. So this works out to 566 Kelvin. Okay, so now I want to do the same thing, only we're going to use van der Waals instead of the ideal gas equation of state. So we're going to follow the same steps again. So we're going to calculate V1 using van der Waals. Then we're going to calculate V2 from the relation that we got, because this is a polytropic process. So V2 is equal to V1 P1 over P2, 1 over 1.2. And then we're going to calculate T2 from van der Waals. Okay, so let's do this. So the van der Waals equation of state looks like this. So if we're calculating, we're calculating V1, so we need P1 plus A over V1 squared multiplied by V1 minus B is equal to RT1. So, and then we have these two constants, so A and B, so we need to calculate those. And they're equal to, so A is equal to 27 R squared, that's the gas constant, multiplied by the critical temperature squared, divided by 64, multiplied by the critical pressure. And B is equal to the gas constant multiplied by the critical temperature divided by 8 multiplied by the critical pressure. So A is equal to 27 multiplied by 0.1889 kilopascal meter cubed kilogram Kelvin. And this is squared, multiplied by 304.2 Kelvin squared, divided by 64, multiplied by 7.39 times 10 to the third kilopascal. So this is going to work out to 0.188 meters to the sixth kilopascal kilogram squared. And the units are kind of weird, but just go through and verify it and make sure that your units are right. So B is equal to the gas constant multiplied by the critical temperature over 8 multiplied by the critical pressure. So this is equal to, 0.1889 kilopascal meter cubed kilogram Kelvin multiplied by 304.2 Kelvin divided by 8 multiplied by 7.39 times 10 to the third kilopascal. So this works out to 0.000972 meters cubed per kilogram. So now what we're going to do is put A and B into this equation, and we know what the pressure is, we know what the temperature is, and we know the gas constant. So we just need to solve this equation for V1. And so let's just write this out. So P1 is 1 times 10 to the third kilopascal plus, and then A is 0.188 meters to the sixth kilopascal kilogram squared, and this is divided by V1 squared, multiplied by V1 minus V1 minus B, which is 0.000972 meters cubed per kilogram. And this is equal to R, which is 0.1889 kilopascal meter cubed kilogram Kelvin, multiplied by 473 K. So what we want to do is solve this. We want to solve for V1. So probably the easiest way to do this is to use solve on your calculator if you have a TI. If you don't, you're going to have to solve this some other way, either using trial and error, or you could write a program to solve it. So once you solve for V1, V1 is equal to 0.08821 meter cubed per kilogram. So now what we're going to do is step 2, where we're going to calculate V2 from V1. And we know that this is a polytropic process, so we know the relation between the pressure and volume. So V2 is equal to V1 multiplied by P1 over P2 to the 1 over 1.2. And this is equal to 0.0, so V1 is 0.08821 meters cubed per kilogram. And we have 1 megapascal over 3 megapascal. And this is 1 over 1.2, which is equal to 0.0353 meters cubed per kilogram. So now we have V2. What we're going to do is plug this into the van der Waals equation, basically the same way that we did before. So we're going to plug V2 into the van der Waals equation, and we're going to solve for T2. So let me just rewrite this over here. So the van der Waals equation is going to be P2 plus A over V2 squared multiplied by V2 minus B is equal to RT2. We're looking for T2, and we know V2, we know P2, and we know A and B because we calculated them previously. So A was equal to 0.188 meters to the sixth kilopascal kilogram squared, and B was equal to 0.000972 meters cubed per kilogram. So if we plug these values into the van der Waals equation, we get the P2 is 3,000 kilopascals, or 3 times 10 to the third kilopascal, plus A, which is 0.188 meters to the sixth kilopascal kilogram squared, divided by V2 squared, which is 0.0353 meters cubed kilogram squared. And then this is multiplied by 0.088 So this is multiplied by V2, which is 0.0353 meters cubed kilogram, minus 0.000972 meters cubed kilogram. And then this is equal to R, the gas constant, which is 0.1889 kilopascal meter cubed kilogram Kelvin, multiplied by T2. And we're solving for T2. So if we go through and solve this, T2 is equal to 573 Kelvin.